Hey guys, this is Mainak, your civil bro. So today I'm going to design, a temple in. This is a ground floor temple in Tekla Structural Designer. Usually I do my recent projects in StatPro and RCTC combined, and then detailing in AutoCAD. But this one I'm doing in Tekla Structural Designer. I do prefer Stat and RCTC mainly because the report generation is good. You know which loads are there, which members are passing, which members are failing. But in Tekla Structural Designer, always there is a kind of an error or warnings in some reports. So when you go for vetting or when you have to verify that your drawing is you've done everything properly, it's difficult to do it. So that's why I don't use it recently. But in this project, I don't need to verify that. I only need to satisfy myself on that uh, whatever sizes I'm getting for the members are okay. So that's why I'm using this Tekla Structural Designer, and also you'll get a way to revise this and also have an experience of practical project. So make sure you like and subscribe. Okay. So this is a basically this is a ground floor building. So this is a Shiv Mandir, and this is the 3D of that particular mandir. So uh, we'll have roof here. This is the ground floor. We have the plinth beams are already constructed. So now they are constructing the columns. Okay. And the person who is constructing he has taken from this taken up from this plinth level. So the column was already there, the foundation was already there, so we don't have a say in that. The column will be same, plinth beam is already done. Now the columns are going up. So but we have a say in the roof beams. So mainly we have to check the roof beam sizes. Okay, and we can also give the slab reinforcement details and also the roof beam sizes. So these two things mainly we have to check here. And as is, we have to limit ourselves to the data which is available here. The height of this mount is 8 feet, and this one is 3 feet. And if you look in the structural drawing, okay, this is the shibling, and we have the murtis here. This is the side entrance, and this is the main entrance. Okay, so I guess this is the main entrance, right? This is the main entrance. Okay. uh, okay, main entrance, side entrance. Okay, so this is not much important because plinth is already designed. We don't have to consider any loads for this level, but the main thing is, okay, this is the column layout plan. The column layout plan. In front there are two columns, I think. Yeah, these two columns are that in front. Okay, all these have been given by me by the architect. And tin beam details and roof beam details are also there, but we have to check this. Okay, roof beam details are okay or not. 220 also, 320 also for B1 and B2, and they have already that, but we have to check. So these are plain beam details, nothing much to check in here. But since it's already been constructed, but roof beam we need to check. Now the main thing which you need to check is already we have this primary beam. So in the primary beam there will be no wall, as you can see. So there will be no wall load for the parapet wall also. But we have to roughly calculate the load of this shrine, if you can call it, this shrine and this shrine. This is approximately pyramid shape, and we have to apply, I think, live load. Not live load, actually a form of a dead load in the form of an area load here. So we'll provide an area load here, an area load here, so approximately we'll get it. And we cannot give any type of beams here for that purpose. So we need to give a flat beams we can give. Okay, or inverted beams also we can give here. Okay, so those things we can do, because in the mandir, in the ground floor, we don't want any beams hanging. So that is the thing, that is the details of the project. So let's go ahead and complete our steps, our duty for to design this project. So yeah, this is in Fate. Yeah, so Tekla does have way of importing center line in feed. So I think I don't have to worry about that. So I'll just first of all I'll save this file, and I'll make another copy of this file. I'll do save as, and this will be CL for TSD. TSD is the short form, Tekla Structural Designer. Always I save in AutoCAD 2000 format, so that everyone can access my drawing whenever required. Okay, this is also there. It's 12 feet 6 in this 3 feet 3 feet here. Okay, this elevation is also there. So from this, actually I can approximately calculate and put the height of the, sorry, load of this in the do for the Garbhagriha. Okay, so this I can do. So this is center line. So I'll just delete most of the things here, right? Most of the things in the plinth, I think only there are main beams, plinth level. Okay, even if none is not there, I not concern too much about the plinth level. Okay, this is done. And this one, let me just delete this. And first of all, delete. Okay, will I have to delete this? Because okay, these my extension is up to here, right? So yeah, I can delete this and delete this as well. And delete this whatever writing we have, and text, right click and we'll do select similar and then delete the text. And then the dimensions, right click and then select similar and then delete the dimensions as well. And here, okay, so center line, whichever we need to give, let's give the center line. ABCD we don't need right now. Tekla will give the ABCD whatever is required. Okay. So these are all the column center lines. So you need the center lines for the beam as well. First of all, I'm putting everything in the zero layer. So there are a lot of layers. This is an architectural plan, so obviously it will have many layers. Okay, but if you take this much layers in Tekla, it will create problems. So I'll okay. First of all, let me extend this EX enter, because yeah, this one or this one, which will let me extended. Yeah, this one will get extended, right? This is the this one will get extended. This one beams. Okay. Let's extend everything. I think these are in blocks, right? Explode the blocks. Explode these blocks, and again just do everything extend for now. And after exploding, now we can do this. So these steps are necessary. That's why I'm showing you. Otherwise, it creates problems. So this after this is done, we use the command ladle and name. Go to name and start deleting, right? Or else just select everything, planters grid, whatever we have except zero, flooring, landscape, window thick, RCC column, RCC, BC, beam, color hatch, color mat, column. Okay, so we're good till now. Let's go forward and again ladle and delete the remaining things. A glass, a hole, a cover. Tab points, okay, tab points you need to keep, right? DM, grid, dimensions, door, format, FTG. So these steps are really necessary because I'm going to import it directly. Again, I'll use ladle. I'm just using doing this in parts because if anything disappears, so I know for which deletion this disappeared, right? Okay. So I have my AH wall. Okay, AH is the connector current layer. So I'll make this current layer this one and use ladle again. And I'll use delete this AOH wall as well. Done. So now I am good. I'll save my project using Control plus S. So this is saved, and when this is saved, we can work on our center line. Okay. I'll insert a layer called CL, and this will be my center line CL, and I'll give a different color and nothing much. Okay, these are my center lines, so I'll put them in CL, right? So this is once this is done, now just need to make the CL for the other beams which the architect has provided, right? So I'm just making sure these beams are at the center. So I'm just using some marking points, perpendicular ones. So I'm just doing these things, and yep. So these are okay. These are in the same line, so I don't need to give them again. And I think I have all of them, I guess. Yeah. So this is like this, copy, and then just paste it here, one here, and one up here, right? And similarly, we'll select this and copy, and do one here, do one here, and one here, and one here. Okay. So this is select this EX center and extend if we have anything, and we can always use this as line and then trim the things which are not in the same line. And similarly, okay, yeah, I think there is a extension here also. I missed that, or I deleted that. So let's see the original file and figure this out. Okay, yeah, this is an extension as well. After this beam, there is one 4.5 feet. Okay, I think it is there, 4.5 feet. Okay, this is 1 feet 5 inches. So it is there actually. So I'll just mark it here up to like this, right? Center line, I'll extend this a bit, and this will be in the same, I'll keep it in the same zone. So EX, enter, center lines, all the center lines we can extend. So done. So done this thing. So then you can delete this once this is done. Okay. So after this has happened, you can delete this also. So just make sure the center line is nice and good at this point. We'll just do that, and because I don't want the any extra things, so I'll take a 90 degree here and trim this as well, and delete this later. So yeah, made sure the center line is okay. And now we'll check whether any center line is missing here. So first of all, we can give a center line here. So what is the size of the beam which we are providing here? So this is a 1 feet beam. So 1 feet beam may actually means you have 12 inches. So actually it is around 300 deep beam, which is there. So for this cantilever portion, as you can see in 3D as well, there is no significant amount of load here, no parapet and all. So I'm assuming a 250 beam would be sufficient in this case, or a 10-inch beam. So my center line, I'm putting it 5 inches from offset from here. So offset 5 inch, offset from here, and I'll just copy this line here because I'm assuming that we'll get a section pass from uh, 5 inch, so 10-inch wall. And similarly, this portion is too close. I don't need to give a a beam here because it is too much close and there is no significant load. So I'll just place this up to here. This beam can go up to there. Okay. So this is the case, and we have pretty much covered all the centerline aspects, I believe so. Okay. So okay, yeah. So I think this is done. Center line is done. So let's see if Tekla has imported this properly or we have to change anything. So this is done, and I will just select, we'll go for the command dxf out. Okay, and CL for Tekla THD, same file, but it's in dxf format. Okay, and go to Tekla. Before opening Tekla, just first make sure that you have a new file. Okay, And then in this new file, we'll just go and we'll go to uh, first of all, we'll go to construction levels and we'll just insert level below. We don't know exactly the plinth level height, but we will see standard of minus 1.5 meter, the plinth level. And we're going to see the heights from our architectural plan and elevation, which is very nicely done, as you can see here. So it is 12 feet, the height. So if you convert 12 divided by 3.28, you'll get in meters, which is 3.65. So this is actually spacing. It is a 3 point. No, this is zero. Sorry. Okay, to do it again. Insert below, and this will be minus 1.5, and insert above, and this will be 12 feet. That is 3.66. Okay, 3.66, and this will be a slab. I'm assuming that the slab thickness will be 150 mm, because this anyway there is a load, kind of load here, and if we do 150 mm, then I think it will be good. Okay, basically you can see the spans here also. It is 20 feet span, and this is a 16-feet span. So I'm going to go for 175 mm slab, and okay, 175 mm slab, yeah, and click on OK. So this drawing unit is in inches. I didn't check. Okay, this drawing unit is in inches, so we need to just import in inches here. So that was a mistake. So we'll go CL3 here and do it again. And this unit this time we'll do it correctly, inches, and only the center line. Okay, and then next these two levels by layer, finish. Yep, and then this import DXF CL3, and then we have as a shadow unit again is inches, and only this time except the center line we want remaining things as our shadow. So now it should be okay. So we'll measure here. So this checking is very important here. 0.305. So it's okay. 300 mm beam. Okay. So this is okay now. Okay. Now we can finally proceed for the uh, putting the column positions and all. So first of all, we'll do the columns, and column sizes from here. This given, and we need to convert this. So let's go forward in this. So this is C1, 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 only point one is C2. Okay. So C1 size is 1 feet into 1 feet 8 inches. 1 feet into 1 feet 8 inches. So it will be approximately 300 into, so if this is 1 feet 8 inches exactly. So it will be 300 into 500 approximately. So we'll go here, columns, and column, and this will be on the size, we'll define this. Breadth will be your 300, and this will be 500. Okay, and AP500D is okay. 40 mm cover, M20, let's go with M20 only now. So, and again, this align automatic alignment, I'll turn it off, and we'll put it at the center. So it's perfectly put. These two places, this one place, this one place, this is another place, this is another place, and we have there, we have here, we have here, and we also have, okay, these two are, I think, I have to press Ctrl plus Z. These two are of different sizes, I think. Let's see. Yeah, these front two are of different. No, these are same size. From the front we have different size. Okay, these two columns we are having, and then next we are having this size. So let's see this size here. It is 9 inches, and It is 1 feet 6 inches. It was 10 inches, right? Yeah, it was 1 feet. So 9 inches means approximately 9 into 20, 25. That is 225 mm. And 1 feet 6 inch means 150 plus 300, 450. So this is 225 into 450 mm beam. So let's do that. 225 into 450 in the THT, and we'll do here. We'll click on escape here, just, and then we'll do here new type of column 225 into 450. Okay, so okay, automatic alignment, I think it is turned off, right? So we'll place at the center now. So this is done, and once this is done, we'll just click on escape. We'll just see the structure 3D here. So this is the structure 3D. So one thing which you need to do is just you do this in step 2 as well. Select all the supports and make them all as fixed. Okay. So this is done. So this is done. Let's go for the plinth beam. So here we'll join only the main beams for the plinth level. Okay, we have the secondary beam positions as well, but we'll join on the main beam. So beam, and here beam size. Let's check the plinth beam size which they've provided. Let's see. This is the PB1 and PB1 and PB2. Okay, everything is PB1. That's good for me. It will be easier. So let's see what is PB1. PB1 is actually a 12 inches into 18 inches beam. So 12 inches means it is actually your 300 mm, and 18 means this will be actually 450 mm. So 300 into 450 plinth beam will be there. Okay. So 300 into 450 will be on pin beam size. Select beam and select the sizes. Click on new. This will be 300 and this will be 450, and we will join all the main beams for now. Okay, I think up to here now. Let's join this. Let's see what happens. Okay. So main beams are joined, and since it will be an extension here, so extensions will also have to be done in the ground floor as well. So we'll extend this up to, yeah, I don't have a line here, forgot to give one. Okay, no problem. If you have, let's do this first and then we'll solve this issue. Beam, and the size. So if you do the secondary beam first, it is more preferred. Okay, I'll tell you that. This thing will solve, but this one, I'm just taking this beam and I'll join it from here to be more sure of the 90 degree, right? Okay, so this is done, and we'll have join this as well. We'll need a beam here as well. There will be some warning here due to such close beam in that region, but okay, it's okay. Okay, let's give this up to here for now, right? No, why here? Let's do this. Let's do this, right? Let's do this. Okay, so here we'll select this, and grid items, architectural grids. Just select. We'll try to select this grid only. So select this. All is selected. I'll try this grid item line 7 items. Then click only this, and now only this is selected. We'll go, edit, and we'll select this copy, and we don't find any reference node here. So, okay, we'll not do this process. Let's go model, and these are the construction line. These are the grid line, right? Parallel quick. Let's select this option. Let's select this and let's keep it here. Okay, we can give the distance here, so it is easy. So let's check the distance from AutoCAD and give it here. So from the center, it is actually 1 feet 11 inches. So exactly, let's convert 11 inches. 11 total there is 12 plus 11. So totally in inches, it is 23 inches. So 23 into 25.4, it is 584.2. Okay, so 584.2. So it is, point. So just click F2, then you'll be able to edit this 0.584. So this is done. Escape. So this grid line is done. Now we can continue with our beam. Let's check the size. It's okay. So we'll continue with our beam. Let's finish this first. There will be a beam here. Right. And then we can do this. Done. And we also need to join this as well. Pin level. Technically, but actually practically this will be very close, so we may leave that as well. Okay, so this is the plinth beam, and this is all for the plinth level. And let's copy this to the roof beam, or we shall do the roof beam separately. So that's up to decide. Let's see. So roof beams, we have to add this. So if you just do from this, you'll not find these points, some points which are required. So we have to make the secondary beams first. Okay, that's why we need to. We cannot copy this, right? Okay, so let's go to the next level. We go to construction levels. Sorry, not construction levels. We go to home on, and then go to structure levels, structure one. Okay, nice and good here. Let's finish the secondary beam. So that let's import the this DXF again. Okay, so let's see what the roof beam size the architect have given, and we'll try to just make that side only. So roof beam details is 12 inch into 18 inches and 12 inch. Okay, same size roof beam. Interesting, very interesting. So 12 inch into 18 inches roof beam size. Good. Okay, they have only changed the rebar. I guess 16 here and this is 20 here. Okay. Okay. So a beam size will be same, 300 into 450. So let's check this out. Okay, let's join this. We have to change this little bit. I'll just tell you. If you are a regular viewer of my Tekla series, you know what, and you have practiced regularly, you know what thing will do. Otherwise, it will be error. So you'll select this, and this is a node. So one node here, another node in this joint. Now it is good. Select this, one node in this joint, one node in this joint. Now it is good. Select this one, select this node, and another node here, one node here. Now it is good. Select this one node here, and one node here. Now it is good. And see, this is perfectly okay. I think this is not. Then this, let's do this from the beginning and keep the nodes in the centers. One node here and another node here. Select this, one node here and another node here. So these are kind of secondary beams. So select all of them and their releases, end one and end two, stiffness and one and stiffness and two we are having. So this is the my stiffness and one value fixed, my stiffness and two value fixed, stiffness and two value stiffness and two value fixed, and stiffness and two value fixed. So this is one and two and two. Okay. So let's just select one. Okay, then it will be simpler. Go to releases and then fixity and one, pin, fixity and two, pin, right? Then this one also. Okay, this, let's select multiple this time. Let's see if this works. And releases, fixity. No, this is not possible. We have to do it individually. Fixity and one, or you can double click also and do this. Releases, span one, make this a spin, and span two. Okay, and this one, I think you don't need to extend this, and double click, releases, span three. This will be pinned. So like this, let's check this was this one also pin and span two. This is okay. This one, these small things you need to do. There are no shortcuts. Okay, done. For the roof beams, it is done. And then we just go and give the other beams. Okay. Let's finish horizontal first. Let's not confuse things. Okay, so now this is done actually. Let's validate. I think there will be some errors. Yeah, I guess there is a member intersection error here and here, as expected, kind of. This was expected. Okay, but ultimately we got only one error. Now it should be good. Let's validate. Yeah. Okay, now it's good. Structure 3D. Yep. So let's go slab, and 175 minimum will require. Okay, let's design one slab here in Excel. Let's take the maximum span and then we'll see what comes the rebar. Okay, this is the maximum one. Let's go. Okay, slab span of the slab, long span and short span. Long span is this the AutoCAD file. Long span is 16 feet 5. So it is 16 into 16. Let's do 16.5. 16 divided by 3.28. Long span is around 5 meter. 5 meter. Short span of the slab is around 14 feet 2. Let's do 14.3 divided by 3.28. It is around 4.35. Let's do 4.4. So yeah, 175 is required. 175 minimum is required. So yeah. So slab depth, overall depth, 175, normal two-way, and we're providing this all. This some slabs will be one way, but one way you cannot design in Tekla one anyway, so no problem. Just take the load into consideration for the main purpose. And check the 3D. This is done here. Now for the loads. So I'm going to provide load of 14 in the plinth beam. Let's do that. Standard loads. So 14, or you can calculate also. I'll just show you the calculation also for the load which we are giving here. So the height, this is actually in the 1 feet wall, means 300 wall, and the height will be, the height is 3.6, and the beam depth, minimum beam depth which you are getting is 3.6 minus these minus, okay, the beam which will be coming after the 450 minus this depth is beam depth is second, this beam size is This beam size is 450. Okay, so 175 mm slab. So 170 or 450 minus 175. So it is 275. So we'll deduct 275 from 3 3.6. So 3.6 minus 0.275. It is around 3.3. So if you do 3.3 into 20 into zero point 0.3, it comes around 19.8 if red brick is used. So this will be the load here, 19.8. So load, dead load, UDL, full UDL, and we go 19.8. Obviously, will not provide along the cantilever portion because there is nothing there. As you saw, only the inner portions we are having this loads. Okay, so this is it, and then we'll go to the next level. The next level. Okay, so let's apply a standard live load because anything will not be there actually. So first of all, let's apply a standard imposed load of 2 here, level load of 2, and apply that 2, and just put it here. And then for the dead load, I'm going to calculate. So there is no parapet wall and all, and but I'll provide an overall load based on the elevation. So we have to do an approximate calculation here. Okay, so we need to calculate this height here. So for calculating the height, we'll use a simple formula. We'll just take the running length, running meter length, okay, and then find the volume of concrete here. Go aligned. Okay, running meter, I think, oh yeah, running meter, it will be a little bit more. Okay, so this is 8 plus 10 4. So it is actually 12 feet, 12 feet, and 4 plus 8 is equals to 12. So it is actually 13 feet. 13 into 2, it is 13 into 2, it is 26. Okay, 26 feet plus this thing, it is 2 feet 9 inches and 9 inches. So 28 feet 9 inches is this running meter length. So 28 feet 9 inches, right? So running meter length, okay, is equals to, just forget this dia cylinder and okay, height 28 feet 9 inches. So it's equals to, convert this approximately, let's take 28 point so let's say 28.8 divided by 3.28 is equals to 8.78. So it is 8.78 meter. So 8.78 meter equal, if you convert this, the thickness is actually 6 inches, 150 mm. So concrete volume which will be required in this is equals to, it will be 8.78 meter into 0.15 and 0.15 meter, and it will be equals to 8.78 into 0.15 is equals to 1.317 m cube. So this will be the concrete required, and the concrete unit weight of the concrete will be 1.3 or 1, let's take 1.4 into 25 kilonewton per meter cube. So 1.4 into 25 is equals to 35 kilonewton per meter cube. If this force is applied uniformly, this will be the load, and the surface area of base which is present there. If you just divide this load into the entire surface area, you will find this. Let's see. Diameter of this is, if you do this pi by 4 into 9 feet square, so it will be actually so let's take base, let's take dia 9 feet. Dia is equals to 9, means 9 into 9 divided by 3.28 is equals to 2.74 meter is the dia. And so 2.74 meter is the dia, and pi by 4 into d square. Area is 2 pi by 4 into 2.74 square. So pi by 4, just calculating this, into 2.74 square, it will be 5.6. It is actually 6. Let's take approximately 6 meter square, and we divide 35 by 6. So load is equals to 35 by 6. It's approximately equals to 35 by 6 is equals to 5.83. Let's take 6 kilonewton, or let's take 5.8 only, because we've taken already a lot of approximations for this. Let's take 5.8 kilonewton per meter square. This will be the load for this one. And for this one, let's take the next one. Next one also, the running meter height. Let's see, calculate. Okay, let's see. 1 feet, 1 feet. Okay, everything in step is 1 feet, I think. Yeah. So running meter length, same thing will copy here. Running meter length is actually running meter length will just copy the same thing for the next structure. Next structure which is made here. So running meter length here is actually uh, 1, 2, 3, 3, 3, 6, and 9. It is actually 9 feet. Okay, so it is 9 feet for the next structure, and is equals to 9 feet is equals to 9 divided by 3.28 is equals to 2.74. And let's take 2.2 let's take 2.74 meter, and concrete volume will be 2.74 into 25. Let's take 68.5. It will be 60. Okay, sorry, concrete volume will be 2.78 to 0.15, because 0.15 is the thickness. 2.78 to 0.15, 2.74 into 0.15, it will be is equals to 0.41. So let's take this 0.5 mq, 0.5 mq, and concrete unit will be 0.5 into 25, right? So 25 into 0.5 is equals to 12.5. 12.5. Now the area. So the area here, let's see what will be the area according to this. So the area here, if we consider a cylinder, let's consider cylinder 7 feet cylinder. So D as surface of base. Okay, let's see here. Diameter is 7 feet here. 7 feet here. So 7 by 3.28 is equals to 2.13. So 2.13, and area is calculate pi by 4 into 2.13 square. It will be a 3.56. So area, let's take 3.56. If we divide the load, divide by 12.5, 12.5 divided by 3.56, and 12.5 divided by 3.56 is equals to 3.51. So 3.51. So this is the load. So in Tekla, let's apply the load here. So we'll go here, take lead load for sure, and then we'll go with this area load, and then the load which you calculate for the top structure, that is 5.8. So we'll put 5.8 here, 5.8, and then apply in the places where it will be there. And then the next load, which is calculated as 3.51. So we'll just go 3.5 and put it here. So we'll just put these things here, and then we will okay, so the load is put here, and then what we'll do, we'll just see if the structure in the structure 3D view. Okay, and then see the loads here, dead load and the imposed load, right? So dead load and imposed load is there. Now in this thing, what we need to do is we need to go to load and add some load combinations. Okay, earthquake load, if you want to provide, you can provide. Okay, or else you can just add the load combinations as well. So let's add the earthquake load as well here, or let's first design without earthquake load first. Add the load combination and add, and okay, not add, just go to load and load combination and click on generate, and then next, and then yes, so column reinforcement, first of all, let me check here very quick. 6 bar of 16, and what we have provided here in this column, 1 2 3 4 5 6 7 8, 8 bar of 20. Okay, this is by the way, minded is not earthquake load, not even considered here. Beam size, beam reinforcement, what is 6, select static, 3 8 16, 5 8 16. Okay, 5 8 16 is maximum, right? 5 3 8 20, so 320 is the maximum. And what are we providing? 320, so beam is okay, 320, perfect. And okay, so these are the beam sizes which have come here. So let's see if we can make this beams, these beams as, first of all, let me try in this particular load. So let me just see if these beam sizes, these all flat beams which are there, if they pass, if we give the normal size which the architect has requested. Okay, so all these beams, the criteria is that it should not hang, first of all. So let's see if this is possible here. This is 300, and we'll go uh, here. First of all, we'll go 250 into 175. Let's go. This is the beam which is included in the slab. We guys know, and then we'll just right click and then design selection. So failed as usual. Let's check selection static. What is the check which is inadequate for torsion? So section is inadequate for torsion, and which means we have to do inverted beams since we cannot go downwards. So let's try inverted beams here. 250 into 250, right? 9 inch means 275. So we can go 250 into 275. So 275 into 275. Let's go. And then right click and then check selection static. So still the section is inadequate for, okay, tension is passing, compression is passing, bar limit it is failing because 220 is coming and this is failing by, you know, bar limits. So if we do, let's do 300 and let's see if the bar limits can, you know, it can pass by bar limits as well. So bread 300. Let's see this one. Okay, it is passing, but bar limits, by bar limits, it is failing. You cannot, 220, it is passing actually. By bar limits is failing, but 300 into 275 into 300, it is passing. 220, it is coming, and by bar limits, it is failing. So it is okay. For now, that's all in this particular video. In the next video, I'll also make another plan and show you in detail the entire process of this THD. But here you have solved an actual project along with me. It's kind of a blog. So make sure you keep learning. Bye bye.